Zooming far enough into a digital photograph, the illusion of a face or landscape dissolves. The computer only sees a grid of isolated gray squares. Each pixel is a single numerical value, completely blind to its neighbors. If we process this image one point at a time by making every individual pixel 10% brighter, we only change the overall exposure. Point processing cannot recognize shapes, detect edges, or resolve fine details because it ignores the spatial relationships between adjacent pixels. To provide that missing context, we use a neighborhood operation. Instead of analyzing a single point in a vacuum, we define a small grid, typically a 3x3 rectangle, around a central pixel. Once we have that neighborhood, we apply spatial filtering. We pass a specific mathematical matrix over the grid, calculating the values of the surrounding pixels to compute a context-aware value for the center point. If we simply average the values in that neighborhood, we get a smoothing filter, which blurs the image. Our objective, however, is the opposite. We want to find and amplify the high-frequency details, the sharp transitions that define texture and boundaries. Image sharpening is not an arbitrary contrast slider. It is the rigorous application of spatial differentiation. To make a computer recognize a sharp edge, we must teach it to calculate the exact mathematical rate of change across a discrete digital grid. In digital image processing, differentiation measures how rapidly pixel intensity, the gray level, changes from one spatial coordinate to the next. The most basic way to measure this is the first-order derivative. It calculates the raw mathematical difference between subsequent pixel values along an axis. This chart shows a raw, one-dimensional array of pixel intensities. The left slope represents a gradual shift from light to dark. The sharp peak in the middle represents a sudden bright anomaly, and the right shows a hard step-up in value. This second chart shows the first derivative of that exact dataset. Instead of plotting raw intensity, it plots the rate of change. The gradual slope becomes a constant negative value, and the hard step change registers as a massive spike, highlighting the edge. First-order derivatives successfully detect prominent, thick edges. However, because they rely on basic subsequent differences, they produce wide responses that are too blunt to isolate microscopic details. To locate those finer details, we require a more advanced metric, the second derivative. This alters the logic we use to interrogate the pixel data. The difference lies in its scope. The second derivative simultaneously evaluates the intensity values immediately before and immediately after a given pixel. This graph shows a new one-dimensional pixel array. It contains a single isolated fine point in the center and a hard step change in gray level on the right. Plotting the second derivative changes the response profile. The single fine point triggers a massive mathematical spike, indicating a stronger response to fine detail. At the step change, it produces a distinct double response, a positive spike followed by a negative spike. That double response provides a precise coordinate. The exact point where the line crosses zero between the spikes mathematically pinpoints the absolute boundary of an edge.
The challenge is that images are two-dimensional. We need to translate this calculus into a grid that a computer can process across an entire photograph. The second derivative acts as a mathematical scalpel, designed specifically to highlight the structural features that point processing and first-order filters miss. The tool we use for this is the Laplacian operator. It is an isotropic spatial filter based on the second derivative. Isotropic means the filter is rotation independent. It performs the same regardless of the direction of the edge. To apply the Laplacian to a digital image, we have to approximate continuous partial derivatives into discrete, integer-based formulas. We add adjacent horizontal pixels, subtracting twice the center. We repeat this vertically. Combining them builds the Laplacian equation. Mapping this into a 3x3 grid yields the classic kernel: positive ones on the cardinal directions, zeros in the corners, and a -4 in the center. The -4 in the center perfectly balances against the 4 surrounding positive ones. If this matrix passes over a flat area of constant color, the surrounding ones cancel out the -4, resulting in a sum of 0. The filter only reacts when it encounters a change in value. By mathematically balancing this kernel, we package complex continuous calculus into a standardized 3x3 grid that a digital system can deploy instantly.
With the model built, we can test it against an imperfect optical target. This unedited image of the moon suffers from optical softness. There is a lack of crisp definition inside the craters. We slide our 3x3 Laplacian kernel across every pixel of this image, calculating the second derivative at every coordinate. The mathematical output is an almost entirely black image, punctuated by glowing white lines. This dark output is not the final product. It is an isolated map of structural discontinuities. To achieve actual visual sharpening, we must merge this high-frequency edge map back into the original data. This is a subtractive enhancement method. Because our center Laplacian value is negative, we subtract the extracted edge map from the original pixel array to arrive at the enhanced result. The result of this synthesis is a final, sharpened image, with the craters now rendered in clarity. Image enhancement is not achieved by boosting global contrast, but by mathematically isolating and then reintegrating structural data. Running a filter pass and then a separate subtraction pass is computationally expensive when dealing with massive datasets. We optimize this by merging the original image array and the Laplacian matrix into a single filter kernel with a center value of 5. This achieves the entire enhancement in one step. In medical bone scans or satellite reconnaissance, this single kernel is just one tool. Professional processing requires a pipeline of multiple discrete calculus operators working in sequence. We started with a grid of isolated values. By applying neighborhood geometry, we derived the spatial context hiding within those numbers. Digital vision is not about photography. It is about leveraging the rigorous laws of spatial differentiation to teach a machine how to mathematically interpret reality.